Hello and welcome to this video about induced current. We're going to look in this video at electromagnetic induction and what that is, different factors that affect the magnitude of induced EMF, 3 ways to induce current in a circuit, and Faraday's law. We know from what we've been studying that we can use a battery or a power supply to create potential difference within a circuit. The EMF increases the electrical potential energy of the charges and causes them to move and create a current. So the battery or the power supply gives us this potential difference, and that creates a current. But there's another way we can create current, and that is called electromagnetic induction. We can actually generate current by using a changing magnetic field around a circuit. So how can we change a magnetic field, or what can cause that changing magnetic field? That can be done in several ways. We can change the strength of the magnetic field, the position of it, or the orientation, and that will actually induce a current in our circuit. Just a reminder in case you forgot, EMF is the energy per unit charge supplied by a source of electric current. That was our definition. It essentially refers to the potential difference. It's measured in volts, so electromagnetic induction also induces EMF. So remember, a current generates a magnetic field. Remember, when we have a current running through this wire, we can put our thumb in that direction, our first right-hand rule, and our fingers curl around, showing us the direction of the magnetic field that is being generated. But the reverse is true. A changing magnetic field induces EMF and the corresponding current. So how does the magnetic field change? The first way we're going to look at is that when we have a loop, a circuit loop right here of wire, and that is crossing these lines. So we can be moving this loop this direction. We can be twirling it like this. And as it crosses the lines of the magnetic field, that essentially is a changing magnetic field to this circuit. So this phenomenon might seem a little bit strange. You might wonder, why does this happen? Let's take a look at how this really happens, or why. Basically, if we have, let's say this is our wire. I made a really great big wire, and here's our magnetic field. Remember, the magnetic field is coming toward you out of this screen. That's what the dots represent. Remember from our previous lessons that when we have positive charges moving with a velocity at an angle to the magnetic field, and this is moving with a velocity, the force, we can use our right-hand rule to determine what direction the force is acting on that positive charge. And in this case, the magnetic force would be acting in this direction on the positive charges. The negative charges are going to be experiencing a magnetic force in that direction. So you can see that as this wire is moving through the magnetic field perpendicular to it, you can see that there is a separation of charges due to the different forces acting on the charges in that conducting wire. So the separation of charges actually induces the EMF. If you think about it, the positive and negative charges, it creates a potential difference between the ends of the conductor, just like a potential difference is created in a battery that has the different positive and negative terminals. So essentially, this is producing an EMF in the same way that a battery produces an EMF. What happens if the velocity stops? If you stop moving it and velocity is 0, there is no longer an EMF being produced. So you have to keep moving the wire through the magnetic field to maintain that source of EMF. The magnitude of the induced EMF is going to depend on several factors. Obviously, the velocity with which the wire is moving, the length of the wire, and also the strength of the magnetic field. The angle also is going to affect the EMF. So think about the induced EMF is going to be the very largest when the plane of that loop is perpendicular to the magnetic field. And here, remember, the magnetic field is coming out at us and the plane of that loop is perpendicular to that magnetic field, and that will give us the largest induced EMF. If we are to tilt this, this is supposed to look like the plane is tilting back a little bit. So it's at some angle that is not perpendicular, but it's not parallel either. Somewhere in between, we're going to have EMF that's somewhere in between 0 and the largest possibility. If our plane is directly parallel to the magnetic field, then we have 0 EMF. So we've been talking about moving a circuit in or out of the magnetic field, and let's look at a couple other ways that we can induce current. This is what we've been talking about. When we have our circuit, our loop here, we can move it through that magnetic field to generate a current, but we can also rotate our circuit. So here, if we have our loop perpendicular to the magnetic field, here it is now parallel, or it's becoming parallel, somewhere in between maybe. We're just simply rotating. We're rotating that circuit, and that can also generate a current. And the other way is to vary the intensity of the magnetic field. So here we have simply our the plane of that loop, and it's the same here and here, but what has changed is the intensity of the magnetic field. That will also generate a current. So let's take a very quick look at what Lenz's law states, and I'm telling you this more than anything to simply explain why there is a negative signature on Faraday's law down here below. But Lenz's law states that if an induced current flows, the direction of that induced current is always in such a direction that it opposes the change which produced it. It's sort of an application of Newton's third law and the conservation of energy, and kind of leads us into Faraday's law of magnetic induction, where we can actually calculate a lot of different things. A lot of relationships are going on in this law. We can look at EMF, the number of turns or coils, the surface area of the plane, and the magnetic field, and how long that loop is in the magnetic field. So Lenz's law essentially is the reason that we have the negative value there. It's indicating the fact that the induced magnetic field always opposes the changing applied magnetic field. A couple more things to note about this equation. What is theta? Theta is the angle between the magnetic field and the normal line that is drawn to the plane of the loop. So, in essence, if the plane of the loop is perpendicular to the magnetic field, then theta equals 0. And if theta is equal to 0 degrees, the cosine of theta is 1, and you have the full strength of your magnetic field that is possible in this calculation. Essentially, what this is doing is it is only looking at the magnetic field component that is normal to the plane of the loop. So this is a little bit limited as far as the math goes in what we're going to be looking at. Surface area is simply the cross-sectional surface area of that loop, what it would be. And N is a whole number, obviously, because it's the number of loops in that circuit. And B is always measured in Tesla. And just because this is a different equation, Tesla, we had learned before, is a Newton per amp meter. In this equation, the Tesla would end up being a volt second per meter squared. Let's try an example together using this equation. We have a coil with 25 turns of wire moving in a uniform magnetic field of 1.5 Tesla. The magnetic field is perpendicular to the plane of the coil. Okay, that's nice. That lets us know that our theta is going to be equal to 0. The coil has a cross-sectional area of 0.80 meters squared. The coil exists in the field exits the field after 1 second. It exists there for 1.0 seconds. Find the induced EMF, and then find the induced current if the coil's resistance is 1.5 ohms. So let's write down what we know. N equals 25 turns. The magnetic field is 1.5 Tesla. theta equals 0 degrees. We know the cross-sectional area, and we know delta T. I'm going to use Faraday's law of magnetic induction equation, and I'm going to plug in all my values. And these are the numbers I'm plugging in. I'm going to solve for the EMF because that's what I'm trying to find, the induced EMF. And when I punch that into my calculator, I get 30 volts. I'm going to write it as 3.0 times 10 to the first, because if I write it in that scientific notation, I can express 2 sig figs. And remember, EMF is essentially potential difference. It's expressed in volts. The second part of the question now is find the induced current if the coil's resistance is 1.5 ohms. Remember that equation? V equals IR. You can rearrange that any way you want. I equals V over R, or R equals V over I, but I remember it V equals IR. That way I can rearrange it any way I would like after that. I know V, my induced EMF, is 3.0 times 10 to the 1 volts. I'm going to solve for I, and I'm told my resistance is 1.5 ohms. So now I can easily solve for I, and I get my current at being 20 amps. I'm going to write that 2.0 times 10 to the first amps so that I can express that in the correct number of sig figs. Advanced ideas. What are some applications of induction? You could describe how doorbells or tape recorders use magnetic induction. Maybe you have another idea you'd like to look into. So I look forward to seeing what you come up with, and we'll see you in class.